In this video, we're going to introduce the idea of potential energy, and I'll start with gravitational potential energy. That's something that we're quite familiar with and can see how something will work. For us, if something is sitting on the ground, and often we will choose the ground level as where our gravitational potential energy happens to be, and then we lift up that object to a height that's above the ground, so that we're up here at some height h above the ground, we would say that the amount of work we've done to raise that thing up would be the gravitational potential energy that we've added to it from when it was on the ground. So the amount of work we'd have to do to get that up there, we'd have to overcome the object's weight and just lift it at constant speed while we get it up there. And we'd say that the GPE up here, I'm going to use that for gravitational potential energy, would equal mg, the weight of the object, times the displacement, vertical displacement we had to give it on the way up. Now, in a previous video, I showed that the work that's done by gravity doesn't matter if you go up at an angle or if you go straight up or if you do some kind of a zigzag or anything. All that matters is the change in height between 2 points. And so if we pick some spot to be where the gravitational potential energy is 0, like down there at the ground, then at a height h above that, as long as little g is constant, we'd have a gravitational potential energy of mgh. It turns out this gravitational potential energy is the negative of the work that the gravitational force would do when we lift the object from ground level up to that height h. Now, most of the time, potential energies are defined as changes in things. We usually have to pick some spot to call 0. And for convenience, on a lot of problems, situations, we'll set it to be 0 at ground level. But we don't have to do that. We could pick it anywhere. If we have an object that's starting at table height, we've got a table sitting here, and an object is on there. And if all the action takes place above the table, we may as well let the gravitational potential energy equal 0 at the top of the table. Now, the book won't use GPE to stand for gravitational potential energy. I just find it kind of handy to do that. It might use the symbol capital U and maybe just put a grav as a subscript on it or something like that. Means the same thing. So there's gravitational potential energy. And the first problem I want to do is one where we're going to use that and an idea called energy conservation. If we don't have air resistance, and here we're going to ignore air resistance, the mechanical energy of the system will remain constant. And by mechanical energy, I mean the sum of the potential and kinetic energies. Sometimes we may have more than just one potential energy acting, like if we've got gravity and a spring acting at the same time. So here's a situation. A punter kicks a football with an initial velocity of 22.5 meters per second at a 46-degree angle with the horizontal. The ball leaves the punter's foot 1.86 meters above the field. What will be the maximum height reached by the ball if you can ignore air resistance? Okay. Well, before we would have treated this as a projectile motion problem and solved it that way. A few days ago, I did a projectile problem where I used work and the work kinetic energy theorem to figure out what's going on. But let's do the same thing here, except let's use the idea of gravitational potential energy. Now, we're going to start off here. We'll have this punter with his foot out there, and the ball is leaving the punter's foot, and we're interested in the instant after the ball leaves his foot and just how high up in the air that thing is going to get. And then it's going to come back down to ground level here. I'm going to let the gravitational potential energy be 0 here at ground level. So GPE equals 0, because we want the maximum height reached by the ball. So we'd like to know, what's this height h? Well, it starts off at an initial height there. And let me show you how I'll take into account the energy here. And when I do energy conservation problems, I usually start it off with initial energy. This will be the instant it leaves the punter's foot, and then I'll be looking at energy at peak, and the energy will be the same. Okay. So here's the initial energy. It'll have a 1/2 m v naught squared. V naught is that 22.5 meters per second. Okay, so I'll have that. Doesn't take into account the angle yet. I will have to do something with that. But there will also be a little bit of gravitational potential energy at the start. That's going to be mgy initial. And then that energy will equal the energy at the peak. Well, at the peak, the gravitational potential energy is going to be mgh. H is just the maximum height that's reached. Now, there's also going to be some kinetic energy left, because the ball has an initial vertical and horizontal velocity. We know about projectile motion that the horizontal velocity remains constant throughout the path, and the velocity we can split up into two parts. This isn't part of the equation, but it'll equal v naught x in the I hat direction plus v naught y, this is v naught by the way, plus v naught y in the j hat direction. Well, v naught x is going to equal v naught cosine of theta, where this angle is theta here. And so we're still going to have that at the peak. And so I would have some kinetic energy associated with that. 1/2 m v naught x squared here at the peak. Okay, well, these two will get added together. That's my conservation of energy equation. Initial kinetic energy plus the initial gravitational potential energy will equal the energy, kinetic energy at the peak. It still has sideways velocity there, no more vertical velocity at the peak, but it does have this, plus gravitational potential energy up there. So I just have to solve for h. And let's see how we get that. I'm going to swap sides with these things. Mgh will equal, I'm going to subtract this from both sides. So I'll have 1/2 m v naught squared minus 1/2 m v naught x squared plus mg y initial. Okay, now can I simplify that thing? Yes, I can, because these two components are perpendicular to each other, but together they add to give you v naught. Okay, I'll have v naught x in the horizontal direction. This is the initial velocity, v naught y in the vertical direction. And something I can say is that v naught squared equals v naught x squared plus v naught y squared. Okay. Well, let's see. If I do a little factoring here, I've got 1/2 m times v naught squared minus v naught x squared plus mg y initial. Well, v naught squared minus v naught x squared is just going to be v naught y squared. So rewriting my equation here, mgh 1/2 m v naught y squared plus mg y initial. All right, I'm after h. Well, one thing I can do is divide out the m's. I'm not given the mass of the football anyway, but it's in every term, so I can get rid of it. And then the h will equal v naught y squared over 2h plus 2g down there. When I divide this one by g, I'll get y initial, just y initial, actually. Talking, writing at the same time. My occupational hazard. You know, it's squared over 2g. Yep. And y initial, yeah, just y initial. I'll rewrite that so it's not so messy. V naught y squared over 2g plus y initial. There we go. I can just plug in numbers now. Actually, v naught y is v naught sine theta. Didn't write it, but you've done projectile motion problems before. And so it will be 22.5 meters per second sine of 46 degrees. Have to square that. 2 times 9.81 meters per second squared plus that y initial 1.86 meters. I just guessed that might be the height at which a punt leaves a punter's foot, because their foot's a ways up in the air when they kick those things, but I'm not positive. Anyway, in this case, which we've done by conservation of energy here, let's see, 15.2 meters for the maximum height reached. I have no idea how high an actual punt might go. I just made up a value for the initial velocity. I don't know if that's anywhere close. This is probably a pretty weak punt because it doesn't seem like this is very high. But at any rate, we solved that using conservation of energy. That one was kind of tricky. Let's see what else we can get. This is one that some of you saw me do in class, but I'm going to do this with conservation of energy instead and not think about work done. The spring has a spring constant of 42.38 newtons per meter and obeys Hooke's law. Now, Hooke's law is the one that says F equals minus kx, and the work done by a spring, whoops, missed it again. Anyway, pretend that goes through the origin. The work done by the spring was always negative, but the work we would have to do to either compress or stretch a spring would be positive. We'd be displacing the spring in the direction that we're making the end of the spring go. And so we would be doing positive work whether we're stretching it or whether we're compressing it. And when that's the case, now that's if we're stretching it from the equilibrium position or compressing it from that equilibrium position. But at any rate, what we end up with for the, sometimes it's u sub EL, or I sometimes write spring potential energy, it's going to end up being 1/2 kx squared for the potential energy of a spring. If you make a graph of that, what it ends up looking, it's a parabola is what it happens to be. And that may not look much like a parabola, but pretend it is. Anyway, that's the spring potential energy, and we're going to use this expression here. So we have a spring with a spring constant of 42.38 newtons per meter. How far do you have to stretch it or pull it back if its potential energy is to be 1.565 joules. Well, this is just asking if U, elastic, or spring potential energy, is equal to 1.565 joules, that's going to equal 1/2 kx squared. What's x? That's all it's asking. And so we'll just solve this thing. We'll have x squared is going to equal 2 times the 1.565 joules divided by k, which is 42.38 newtons per meter. Now remember, a joule is a Newton meter, so joules over newtons per meter are equal to Newton meters over newtons per meter, and that's meters squared. Okay, but that's what we'd expect for a length squared. So if we multiply this by 2, divide by 42.38, and take the square root, well, let's go ahead and actually calculate that first. Okay, for this I get 7.386 times 10 to the minus 2 meters squared, and then just solving that for x, I would get meters. Okay, then part B asks, what is the mass of a ball at the end of the spring if the maximum speed of the ball is observed to be 2.402 meters per second when the spring is released? So what's going on here is we've stretched the spring by that distance, and so we'll imagine this being a horizontal situation here. So we've got this spring stretched out, and it's got 1.565 joules of kinetic or potential energy in it. And then we attach a ball to the end of it. So somehow or other we do that and let go. Okay, and so this spring is going to pull back to its equilibrium position, and when it's there, the ball will have a speed of 2.402 meters per second. So let's write that as a conservation of energy problem. And I'll just say initial equals final. Well, initially what we've got is 1/2 k x squared, which we know is 1.565 joules. At the end, the spring is back to its equilibrium position. X is 0, but there's going to be kinetic energy. By the way, we assume the spring itself has no mass, or very little compared to this ball that we're sticking on the end of it. And so we don't think about the kinetic energy of the spring itself. That's kind of cheating, but it is what we do. Anyway, at the end, we'll have this kind of energy, and all we have to do is solve for m, because we know how fast it's going. We know that this thing over here is the 1.565 joules. So let's just take it and solve it. 1.565 joules divided by 1/2 v squared is going to equal, if I take that 1/2 and stick it up top, I'll have 2 times 1.565 joules divided by v squared. Well, that v was 2.402 meters per second, and I square that, and I'll get, that's solving for the mass. Now, a joule, besides being a Newton meter, a joule can also be written as a kilogram meter squared per second squared, because that Newton is actually a kilogram meter per second squared. And so we got all these units that are circling around here. So up top I'll have a kilogram meter squared per second squared, when I square this velocity or this speed down here, I'll have meters squared per second squared, which will divide out with the meters squared per second squared in the joule, leaving me kilograms, just what I wanted. So, and I get 0.5425 kilograms, a little more than half a kilogram. All right, we figured out the mass using conservation of energy. One more thing to this. How fast is the ball moving when the spring is pulled back halfway to its equilibrium position? Well, let's do another initial equal final thing here. Now, final in this case is just going to be halfway back to the equilibrium position. Well, again, at the initial position, I'll have that 1/2 kx squared, which I know to be 1.565 joules. The final position here, I won't have zero potential energy in the spring because it's going to have 1/2 k times x over 2 squared. X here is going to be the maximum stretch of the spring, which I don't think we even figured out, did we? Oh, yes, we did. It was 0.2718. But I'm not going to bother to stick that in here yet. I want to show you something. And then I'll have some kinetic energy here. 1/2 mv squared. And this is a different v than what I had up here. I could call it v sub 1/2 or something like that, except I don't want to stick a complicated subscript on here. But I'm going to mess around with the algebra on this thing, and I'll solve for 1/2 mv squared. It's going to equal 1/2 kx squared. When I square this x over 2 here, I'll get x squared over 4. And so I'll have, I'm subtracting that from both sides, I'll have 1/2 k times x squared over 4. And I can factor out that 1/4 there to where I'll have 1/2 kx squared, which I'm going to wrap in parentheses, minus 1/4 of 1/2 kx squared. Well, this is my 1.565 joules minus 1/4 of 1.565 joules. I think that's 3/4 times 1.565 joules there. And so I'll have 1/2. I'm going to finish this on another little sheet of paper here. 1/2 mv squared. I can calculate this thing now. It's going to be 1.174 joules is how much that is. And if I solve for v squared, multiply both sides by 2, I'll have 2 times 1.174 joules divided by that mass, which is somewhere around here, 0.5425 kilograms. And because a joule is a kilogram meters squared per second squared, the kilograms will go away and I'll have meters squared per second squared. For v squared, I get 4.327 meters squared per second squared. Taking the square root, I would get 2.080 meters per second. Notice this speed is not half of that 2.402 meters per second squared. And the reason for that is that when we look at the spring potential energy, couldn't see that, here's the spring potential energy going out to that distance x. Here's what it is at 1/2 x. When the spring pulls the mass from its maximum extension position back to half of that, this area of the graph is 3 times as big as that. It has expended 3/4 of its stored energy pulling the mass from here back to here. And that just the spring force, the way it works is the energy stored is under this curve here. And so that's what happens, and that's why it has a speed that's, wherever it went, there it is, nearly as great as the maximum speed, because it didn't have that much more to add, pulling that extra little bit there. Okay, we got time for another one? I hope so. I may save that one for later. Yeah, I think I'll do those last 2 problems in another video. But this is a pretty good one. It's like an Atwood's machine, except it's asking a question that we never asked of the Atwood's machine. 2 blocks are connected by a light frictionless pulley, as shown in the figure below here. There's a 3 kilogram mass that's on the floor down here, the 5 kilogram mass that's 4 meters above the floor. This is not our Atwood's machine. We had them drop maybe a little more than 1 meter, and so this one may be more spectacular. Anyway, the 5 kilogram mass is released from rest. Use conservation of energy to determine the speed at which the 5 kilogram object hits the floor. Okay, and then what was the acceleration of the 5 kilogram mass towards the floor? We're going to do this without going through the Newton's law derivation that you'll be doing for your lab. So we'll have initial is going to equal final. And let's think about what we have for initial energy. There's no kinetic energy because it's released from rest. I'm going to let GPE, gravitational potential energy, equals 0 at the floor. Okay, so this thing has no gravitational potential energy to start with, but this does. And the initial energy is all going to be that m5 times g, its weight times the 4.00 meters, which I'm going to call just y initial. So m5g times y initial. That will equal the final energy. Well, in the final situation, the 5 kilogram mass is going to be on the floor, so it's not going to have any gravitational potential energy anymore, but the 3 kilogram mass is going to be the height y initial above the floor. So now I'll have m3 g y initial for gravitational potential energy, but both of the masses are going to be moving. This will be the instant before the 5 kilogram mass hits the floor, so it's still 1 atomic radius above the floor, or not much anyway. But what we'll have is plus 1/2 m5 times some speed squared, and the 3 kilogram mass is tied to the 5 kilogram mass by a spring or a string. It's going to be moving just as fast. So 1/2 m3 times v squared, and we can figure out what that's going to be. If I subtract this from both sides, m5g y initial is going to equal, whoops, not equal, but minus m3 g y initial. That will equal, I can factor a couple things out of here. I'll have v squared times, actually I can write it as m5 plus m3 divided by 2. And so I have that. And then, well, let's see. I can do a little factoring on this side. I'll have m5 minus m3 times gy initial divided by m5 plus m3 divided by 2. And I can make that look a little tidier. I'll have m5 minus m3 over m5 plus m3 times 2gy initial. And that will equal v squared. So these things have 3.00 kilograms and 5.00 kilograms. So I end up with, on top I'll have 2.00 kilograms. Their sum is going to be 8.00 kilograms times 2 times 9.81 meters per second squared times y initial, which is 4.00 meters. Oh, this is interesting. 2 over 8 is 1 over 4 times 4. That's just going to be 1. So I'll have 2 times 9.81 meters per second squared, except unit-wise I'll have meters squared per second squared. That's going to be 19.62 meters squared per second squared, and that'll equal v squared. Oh, check me on that math, but I'm pretty sure that's right. So v is just going to be the square root of that. I get 4.43 meters per second. Okay. Now, what about the acceleration of the 5 kilogram mass toward the floor? Well, here's a way to get that. It's this. V squared minus v naught squared equals 2 times the acceleration times the distance it traveled, which is 4.00 meters, or that y initial. It came this way if we think down is positive for that thing. V naught was 0, and so the acceleration is just going to be v squared over 2y initial. Could I somehow have gotten that out of here? I think maybe I could have. V squared, or a is v squared over 2y initial. Yeah, look at this expression here. If I divide both sides of this by 2y initial, what I'll have is, you can get a number for it, but this is more fun. V squared over 2y initial, that's the acceleration. It's going to equal m5 minus m3 over m5 plus m3 times g. Does that look like the mass ratio in the Atwood's machine lab? And our accelerations, the way that we figured it out was to make a graph of accelerations versus mass ratios, and we found out it was g. So that's what we did on those things. And so we could plug in the numbers and actually get a number here, but it would be something like this is what we'd have out of there. That's Atwood's machine, analyzed using conservation of energy. Another thing solved. Okay, I've got a few more problems, or a couple more that we could solve, but I'm going to save them for another video because this is enough for one.